Thousands of meters beneath the Southern Ocean, enormous rotating bodies of water are quietly carrying heat toward Antarctica. They are not permanent currents and they do not appear on a map like the Gulf Stream. They are ocean eddies, swirling structures tens to hundreds of kilometers across. For years, scientists knew these underwater vortices moved heat near the surface. What they could not measure well was what happened deeper down. Now, after analyzing roughly 2 decades of observations from robotic Argo floats, researchers have found that deep Southern Ocean eddies transport heat southward on a scale comparable to the eddies near the surface. Even more surprisingly, they can push subtropical warm water more than 10 degrees of latitude farther toward Antarctica than the average current would carry it alone. This matters because the Southern Ocean is one of the main gateways through which heat moves around the planet. It circles Antarctica without continents blocking its path, allowing the Antarctic circumpolar current to connect the Atlantic, Pacific, and Indian Oceans. It also separates relatively warm subtropical waters from the freezing seas surrounding Antarctica. The question is how heat crosses that moving barrier. If warmer water can travel farther south at depth than scientists assumed, it could influence the ocean surrounding Antarctica and potentially affect ice, sea level, and the global climate system. The discovery begins with a problem that oceanographers have struggled with for decades. Satellites can measure the surface of the ocean extremely well. They can see sea surface temperature, the height of the water, and the subtle bumps created by rotating currents. But most of the ocean is hidden below that surface. A powerful eddy may continue downward for more than a kilometer, yet from space scientists can only infer what is happening underneath. The Southern Ocean makes direct observations especially difficult. It is remote, stormy, cold, and covered by sea ice during part of the year. Research ships can collect detailed measurements, but they cannot continuously survey an ocean covering tens of millions of square kilometers. Before autonomous instruments became widespread, deep ocean measurements were simply too sparse to calculate how much heat eddies were moving below the surface. Then came Argo. The International Argo program maintains thousands of robotic floats throughout the world's oceans. A standard float spends most of its time drifting roughly 1,000 meters below the surface. About every 10 days, it descends toward 2,000 meters and then rises slowly upward while measuring temperature, salinity, and pressure. Once it reaches the surface, it uses satellites to transmit its observations before sinking again. A typical float repeats the cycle for 4 or 5 years. Together, the global array creates a constantly updated 3-dimensional record of the ocean. Researchers used this long observational archive to examine the Southern Ocean from the surface down to roughly 2,000 meters. They calculated 2 important properties. The first was eddy kinetic energy, essentially a measure of how energetic the swirling motions were. The second was eddy meridional heat transport, the amount of heat those motions carried north or south. At first, the deep ocean did not look particularly energetic. Below roughly 1,000 meters, eddy kinetic energy was only about 1/5 of that near the surface. If movement is much weaker, it would be reasonable to assume heat transport should also be dramatically weaker. But it was not. Despite containing far less kinetic energy, the deep eddies transported heat toward the poles at least on the same order of magnitude as surface eddies. This means the deep Southern Ocean is surprisingly efficient at moving heat. The strongest motion does not necessarily carry the largest share of the thermal signal. A relatively weak deep current can still move enormous amounts of heat if it consistently transports warmer and colder water in the right directions. Imagine 2 conveyor belts. The upper belt moves quickly, but the objects on it contain only small differences in temperature. The deeper belt moves more slowly, yet repeatedly carries very warm material one way and colder material the other. The slower belt can still transport an enormous amount of heat. Something similar appears to be happening inside Southern Ocean eddies. The researchers then asked a more visual question. Where does the heat actually go? They tracked the movement of subtropical warm water in experiments with and without the effect of deep eddies. When only the average ocean circulation was considered, warm water followed a more limited southward path. Once the deep eddy transport was included, the warm water influence extended more than 10 additional degrees of latitude toward Antarctica. 10 degrees of latitude is more than 1,000 kilometers. That means the eddies are not simply rearranging temperature inside one narrow band of ocean. They can substantially extend the reach of subtropical heat into higher southern latitudes. The effect was also highly uneven around Antarctica. About 60% of the diagnosed deep poleward eddy heat transport originated in the Indian Ocean sector of the Southern Ocean. This suggests that the ocean does not deliver heat toward Antarctica uniformly. Geography, seafloor topography, the position of major currents, and the intensity of eddies create preferred pathways. This is where the story becomes especially important for Antarctica. Much of the ice around Antarctica does not melt primarily because warm air touches its surface. Some of the most vulnerable glaciers terminate in the ocean, where relatively warm water can reach beneath floating ice shelves and melt them from below. Those shelves act as barriers that slow the glaciers behind them. When they thin, grounded ice can move toward the ocean more rapidly. The new study does not show that one specific deep eddy is currently melting an Antarctic glacier, and it does not calculate a direct contribution to sea level rise. Its conclusion is more fundamental. It demonstrates observationally that deep mesoscale eddies are capable of carrying substantial quantities of heat much farther toward Antarctica than the mean current alone. That means climate and ice models need to represent this pathway correctly when determining where Southern Ocean heat ultimately goes. Why was such an important transport mechanism underestimated for so long? Part of the reason is scale. Mesoscale eddies are huge from a human perspective, but relatively small compared with an ocean basin. Many global climate models cannot resolve every eddy directly. Instead, their effects must be approximated through mathematical parameterizations. If the behavior of deep eddies is poorly observed, those approximations become uncertain. There is also an intuitive trap. Scientists knew that eddy energy decreases strongly with depth. It is tempting to assume their climatic importance must decrease by the same amount. The Argo observations show that this is not necessarily true. Deep eddy kinetic energy may be only 1/5 of the surface level, yet its heat transport remains comparable in magnitude. The Southern Ocean is already central to Earth's heat budget. More than 90% of the excess heat accumulated by the climate system since the 1970s has been stored in the oceans, and Argo observations are one of the main ways scientists track where that heat goes. The ocean interior is particularly important because heat stored hundreds or thousands of meters below the surface can remain isolated from the atmosphere for long periods. But heat does not simply sink and remain where it entered. Currents redistribute it horizontally and vertically. Eddies form where large currents become unstable, peeling away rotating parcels of water that can carry their temperature, salinity, nutrients, and other properties into surrounding regions. In the Southern Ocean, this eddy activity is especially intense because the Antarctic circumpolar current is one of the strongest current systems on Earth. The new observations reveal that some of those swirling structures remain climatically important far beneath the most energetic surface layer. The finding also demonstrates why robotic ocean observations have changed Earth science. Before Argo, ships sampled the ocean along specific routes and usually during seasons when conditions were safe enough for field work. Argo floats now collect measurements throughout the year, including remote regions that ships rarely visit. The standard network contains roughly 4,000 active floats globally and generates vertical profiles across the upper 2,000 meters of the ocean every day. Even Argo has limits. Standard floats do not routinely measure the deepest parts of the ocean below 2,000 meters. Some new deep Argo instruments can descend to 4,000 or even 6,000 meters, which means future observations may reveal additional heat transport beneath the depth examined in this study. That raises an obvious question. If substantial eddy transport exists down to 2,000 meters, what is happening deeper? Scientists do not yet know the complete answer. The newly published research explicitly provides the first observational quantification of deep eddy kinetic energy and meridional heat transport using Argo data, but the abyssal Southern Ocean remains much less observed than the upper layers. Future deep Argo measurements, improved satellites, and higher resolution models may extend this picture all the way toward the sea floor. The broader lesson is that ocean heat transport does not resemble a single river flowing toward Antarctica. The real system is messier. Large currents establish the general circulation, but thousands of rotating structures constantly peel water away, mix neighboring regions, and move heat across the boundaries formed by the mean flow. From above, an eddy may look like a circular disturbance on the sea surface. Deep below, it can behave like a hidden vehicle carrying subtropical heat hundreds of kilometers farther toward the pole. For years, scientists could see only the top of that process. 20 years of robotic measurements have now exposed the deeper half of the story. The Southern Ocean is not only transporting heat through its enormous visible currents. Beneath them, a quieter network of underwater storms is moving warmth toward Antarctica, one rotating body of water at a time.